DatBench, Discriminative, Faithful, and Efficient VLM Evaluations. This paper from the Datology AI team it's a big one. It doesn't just evaluate models, it really critiques the very methods we all rely on, and it exposes some pretty profound flaws in our current VLM benchmarks.
It really does. I mean, the core insight is that up to 70% of questions in some of these popular benchmarks are solvable without looking at the image.
70%. So they're basically just language puzzles.
Exactly. And on top of that, the heavy reliance on multiple choice formats is just wildly inflating model accuracy scores.
And that inflation comes at a staggering financial cost. Evaluation has become this massive computational bottleneck. We're talking nearly 20% of the entire post-training compute budget for some of these big models.
Yeah, if you're an engineer trying to iterate quickly, that kind of compute drain is just crippling.
So the solution they propose is DatBench, and it kind of redefines evaluation as a rigorous data curation problem. It's based on three psychometrically grounded criteria: faithfulness, discriminability, and efficiency.
And by systematically filtering out all that noise and the low signal samples, they maximize the utility of every single test case.
The gains are just wild. DatBench delivers a 13x average speedup and up to 50x in some capability clusters, while, and this is crucial, maintaining the ability to accurately rank the models.
And cleaning up the data immediately exposed these deep VLM pathologies, things like a genuine reasoning versus perception trade-off, and maybe the most surprising thing, an overthinking penalty, where giving models more inference time actually makes their performance crash on simple perceptual tasks.
We're diving into the systematic methodology they use to clean house and rebuild the VLM performance compass.
Let's do it.
Okay, let's unpack this. For all the engineers and researchers listening, when we say benchmarks are failing, what does that actually look like in practice? And why has evaluation gone from being a simple scorecard to this major bottleneck?
Well, evaluation should be the primary compass guiding where you allocate, millions of dollars in compute. But right now, it's acting more like this passive, really expensive reporting tool.
And the paper argues that when your compass is that flawed, you end up just wasting effort. You're optimizing for mirages.
Exactly, things that don't reflect true capability. Or you just grind to a halt because the testing itself is just too slow.
Okay, let's talk about that speed issue. The cost of training models is obviously astronomical, we all know that, but what about this post-training phase? How severe is the evaluation compute drain really getting?
It's becoming prohibitive. I mean, the paper points out that for a model like OLM3, almost 20% of the total compute budget for the post-training development phase, it was just spent on evaluation.
20%, just on evil.
Just on evil. And it's getting worse because of architectural trends, right? You have higher res images, which means dense visual tokens, and models are using these really long reasoning traces for problem solving that can exceed, tens of thousands of tokens.
So we're just throwing immense compute at test samples that might be trivial or noisy or just totally redundant.
We are. Which makes no sense.
That makes perfect sense. So if you're going to invest that much compute, the data has to be pristine. So to fix this, the researchers created a framework built on these three criteria, or desiderata, as they call them.
Exactly. They basically established the fundamental properties evaluation data must have to actually be useful. First up is faithfulness.
Meaning, does the example genuinely require you to look at the image to answer it?
Yes. And it also has to reflect how VLMs are actually deployed.
Yeah.
So generative, open-ended answers, not multiple choice.
Okay, and the second one?
Second is discriminability. This is absolutely key for efficiency. The example has to reliably separate a stronger model from a weaker one. If every model gets it right or every model gets it wrong, it's not useful for tracking progress.
And third, efficiency.
Right. Maximizing the information signal you get for every unit of compute you spend. And DatBench is really all about achieving all three of those at the same time.
And this is where it gets really, really interesting because they started by attacking these mirages of capability. And the numbers and offenders seems to be the traditional multiple choice format. For our technical audience, why is MCQ such a fundamental failure?
Well, multiple choice questions, they just systematically inflate what we think the model can do.
Right.
For one, they introduce a baseline accuracy from just random guessing.
Right, so every model gets a head start.
A non-trivial one, yeah.
Yeah.
But second, and this is maybe more important, they create this huge evaluation deployment gap. In the real world, you ask a VLM to generate an answer. But MCQs let models use shortcuts, like just eliminating one obviously wrong option, instead of proving they truly understand.
And when they actually tested this inflation, the results were pretty dramatic. What was their solution?
They pushed for generative conversion, so they transformed MCQs into open-ended generative tasks wherever they could. Now, free-form answers are obviously hard to grade automatically, so they used a strong LLM as a judge, specifically Qwen 330B, to do semantic matching and scoring.
And what was the score drop like? How significant was it?
It was startling. On the AI2D dataset, the average accuracy across their whole suite of 27 models dropped from about 77.5% all the way down to 40.5%.
Wow. That's a nearly 35-point drop.
It is. And that just proves that the MCQ format was masking this massive gap between a model's ability to select an answer versus its ability to actually generate one.
That's a crucial distinction. But what about tasks where multiple choice is kind of structurally necessary? Like, complex reasoning puzzles? They had a clever fix for that too, right?
They did. It's called circular evaluation. For those MCQs, they run the model multiple times, but they systematically rotate the order of the options. A model only gets credit if it consistently picks the right answer across all of those rotations.
So it neutralizes the chance baseline. It forces the model to rely on actual logic, not just positional bias or something.
Exactly. You get a much steeper, more accurate performance curve that reflects real capability.
Okay, so that brings us to maybe the single most shocking statistic in the paper. This problem of blind solvability. This is where models are answering correctly without even needing the image. How widespread is this?
It's the ultimate mirage of progress because it doesn't reward better vision-language integration. It just rewards stronger language models.
Right.
Their analysis showed that in VQA-V2, which is a foundational benchmark, over 70% of the samples could be solved correctly by a strong LM using only the text.
70%? You have to really sit with that for a second. That's a benchmark failure.
It's a total failure. You're spending all this time and compute evaluating a visual model on a task that is fundamentally not visual.
So to make this really stick, what are the main types of language priors these models are abusing?
The researchers broke it down into the three categories. First is just world knowledge. Think of a question like, how many legs does a dog have? The answer is always 4. Doesn't matter what the image shows.
Okay, makes sense.
Second is visual stereotypicality. If the question is, what color is the stop sign? The model will guess red just because that's the dominant linguistic prior in its training data, not because it actually parsed the color in the specific image.
And the third one?
Purely symbolic reasoning. So something like being asked to count the number of digits between 10 and 20, the LM can just solve that arithmetically. It doesn't need to see anything.
So how did DatBench filter for this? How did they make sure the visual input was absolutely mandatory?
They used a systematic thresholding strategy, which they called TAO. So TAO is the number of models out of the 27 they tested that can solve the question using only the text prompt.
So they test every model blind first.
Right. And the key is adjusting TAO based on the task. For a critical open-ended generative task, they use a super strict threshold of TAO equals 1. If even a single model can solve it blind, the sample is thrown out.
But for noisier tasks?
For constrained or MCQ tasks, where there's some guessing involved, they'd use a higher threshold like TAO equals 5. This whole process ensures that the final dataset is genuinely faithful to multimodal reasoning.
So moving beyond the structural flaws in the questions themselves, let's talk about just raw data quality and efficiency. These are huge hurdles for anyone trying to iterate quickly.
Absolutely. When you pull together data from all these different sources to make a big benchmark, noise is it's inevitable. You're going to have mislabeled examples, ambiguous answers, low-resolution images.
And filtering that noise is critical because otherwise you end up, what does the paper call it? Hill climbing on noise.
That's it. You end up penalizing a strong model for giving a correct answer that happens to contradict a flawed label. It totally obscures genuine progress. Developers waste huge amounts of compute tuning their model to get a better score on a bad sample.
So to fix this, they used this clever 2-stage filtering pipeline with a VLM as a judge. How did that work? It seems a bit meta to use a stronger model to vet the failures of smaller ones.
It's a really strategic way to do it.
Yeah.
So stage 1 was cheap. They just flagged every single example that was missed by all 27 of their evaluated models.
So if everyone fails, it's either a really hard problem or a bad question.
Exactly. It's either a true capability frontier or it's a data flaw. So then stage 2 deployed a powerful proprietary VLM judge, GPDP 5.2 in this case, to actually verify the ground truth of only those flagged samples. If the judge said the sample was ambiguous or labeled wrong or just unsolvable because of low resolution, it was discarded.
And how much noise did this actually get rid of?
A remarkable amount. The spatial capability, which often uses data from autonomous driving datasets, saw a massive 42% discard rate.
42%.
Yeah, mostly because the images were just too low resolution to support the kind of reasoning the question was asking for. Even expert-authored benchmarks like MMEU Pro had almost a quarter of their samples removed.
Wow. So without this kind of verification, almost a quarter of your evaluation effort could just be wasted on bad data.
That's right.
So, okay, the data is now clean and it's faithful. The final challenge is efficiency. How do you select the absolute most informative samples to maximize your signal per compute? Why do standard ranking metrics not work here?
Well, standard methods, like looking at Spearman's rank correlation, they saturate really fast. You can take a random subset of a benchmark, and it'll probably maintain the global rankings, because models fall into these coarse tiers. But that random subset will still have a ton of low signal items that don't really separate the good models from the great ones.
So the goal isn't just a stable ranking, it's maximizing the total discrimination.
Exactly. And this is where they brought in a concept from classical psychometrics.
Right, this point-biserial correlation, or RPB. Can you break that down for us? Why is that a better metric for picking questions?
So RPBD, think of it intuitively like this. It measures how well success on one single question correlates with a model's overall ability score across the whole test. So if a question is so easy that every single model gets it right, its RPB score is near zero. It doesn't discriminate. If it's so hard that every model gets it wrong, RPB is also near zero. A high RPB score means only the stronger models tend to get that item correct.
Ah, I see. So it's basically an information density metric. It finds the questions that carry the most signal about a model's relative strength.
You've got it. And by prioritizing these high RPB items, they achieve those dramatic speedups. DatBench selection got to about 90% of the total discriminative power using only 40% of the full filtered dataset.
And that's what led to the average 13x speedup.
That's it. And up to 50x in areas like general VQA, where the original dataset was just massively redundant. This lets engineers iterate daily instead of weekly.
So as a result of all this work, they released 2 essential resources for the community.
Correct. First is DatBench itself, which is the highly efficient subset for rapid iteration. And crucially, they reserved up to 20% of it for these manually verified, currently unsolvable frontier examples. They have low RPB today, but they ensure the benchmark stays useful as models get better.
And the second one?
DatBench Full, which is just the complete collection of all the high-quality samples that remained after all the filtering. That's meant for more comprehensive error analysis or final reporting.
What's so fascinating here is that when you strip away all the noise, all the mirages, and the redundancy, you're left with this incredibly high-fidelity signal that just immediately reveals these fundamental architectural trade-offs that were masked before.
It's incredible what becomes clear.
So let's start with the capability correlations. What did this clean data tell us about how different skills relate to each other inside a single VLM?
We saw this really tight reasoning cluster. So tasks like chart understanding, math, and general VQA show these exceptionally strong positive correlations. Chart and general tasks correlated as high as R equals 0.90.
So if a model is good at reading charts, it's very likely to be good at general VQA.
It strongly predicts it, yes. It seems like they rely on some kind of shared foundational abstract reasoning skill.
But this high-level reasoning seems to come at the expense of lower-level, more fine-grained perception.
Precisely. They identified a really sharp spatial semantic trade-off. You see negative correlations between a low-level task like grounding and a high-text density task like document understanding or OCR.
So if a model is great at OCR, it's often actually worse at spatial reasoning.
And vice versa, yeah. The data suggests a latent conflict in how we're currently training these VLMs. The model really struggles to optimize for both abstract logic and precise perceptual fidelity at the same time.
Which means certain models are effectively being forced to become specialists. Can you give a concrete example of a model that showed this specialist profile?
Oh yeah, the results make it super clear. So for example, the GLM 4.1v9b model acted like a perception specialist. It was a leader in diagram understanding and spatial tasks, but it only scored 17% in math.
Okay, and the opposite?
The R4b model was the math specialist. It got the highest math score, over 43%, but it had the absolute lowest spatial performance at just over 11%. The true generalists that can do both well are surprisingly rare.
Okay, and the final and maybe most expensive finding is this overthinking penalty. This is the regression you see when you scale up inference compute using techniques that let the model think longer.
This is a massive finding because it undermines a really common scaling strategy.
Yeah.
So scaling inference compute, it does help the reasoning cluster. Math improved by about 37%. But that exact same scaling caused devastating regressions in the purely perceptual tasks.
How devastating.
OCR performance dropped by about 53%. Document understanding dropped by about 48%.
That's a colossal penalty. Why would trying to think harder make a model worse at just seeing things?
Well, the hypothesis is that on these simple perceptual tasks, the model gets stuck in these unproductive thinking loops. Instead of just answering what it sees, the scaled inference process forces it to generate these long, convoluted reasoning traces that just add noise and, ironically, disrupt its ability to output a clean, direct answer.
And I imagine those unproductive loops are computationally just egregious.
They are. A correct thinking answer uses around 400 tokens. An incorrect thinking response, so pure wasted computation, balloons to almost 1,200 tokens.
That's a 14x increase in tokens.
On a task that the model should have just solved directly with perception. It proves that efficiency isn't just about your evaluation data. It's also about your architectural choices at inference time.
So finally, let's circle back to faithfulness, but through this lens of the vision delta, or V delta, what exactly does that metric tell us?
The vision delta is maybe the most honest metric of all. It's simply the performance gap between the full multimodal evaluation image, plus text, and the blind, text-only baseline.
So you can think of it as the score you lose if the VLM essentially just shuts its eyes.
It's the true measure of vision dependency.
That's right. And which tasks really, truly rely on the image, according to this metric?
Tasks like counting and grounding showed a really high vision dependency. They're the most faithful tasks. But contrast that with tasks that showed high language prior distortion, like math, which only had a V delta of 13%.
So that low delta score confirms that even after all this filtering, a high score in math is still mostly rewarding a stronger language model backbone, not necessarily better vision language integration.
That's exactly what it suggests.
So what does this all mean for you if you're out there developing the next generation of VLMs? The takeaway from DatBench seems crystal clear. Evaluation is not a passive reporting task anymore. It demands the same rigorous data curation we apply to training data.
Absolutely.
Yeah.
By establishing this rigorous standard, operationalizing discrimination with point-biserial correlation and forcing faithfulness through filtering to DatBench has delivered a precise, sustainable instrument. They didn't just speed up evaluation, they dramatically increased its fidelity.
Which allows researchers to actually track the emergence of capabilities and identify these true architectural trade-offs without the old bottlenecks.
Right.
And we're learning that discrimination itself is a moving target. What separates models today will be trivial tomorrow, which I think raises a fascinating final question. If the goalposts are always shifting, should we expect future benchmarks to just be these static data sets that eventually get saturated?
Or do we see a necessary industry shift toward dynamic, constantly optimized living benchmarks? This is a concept the authors call DatBench Live, where these high-signal subsets are automatically recomputed, maybe periodically, as model capabilities continue to scale.